All right, you guys ready? Okay. Hi, everyone. Thank you for coming. This is our 11:30 workshop on New Horizons. So I'm going to introduce Jim Green, who will introduce our panelists.
Thank you very much. This is really a tremendous opportunity to give you some background information that is absolutely unbelievable. A few things happened this summer that, to me, it still resonates. It's so remarkable. And it's so important that the occultations that were performed this summer we talk about, because it sets the stage of what will happen next. I'm Jim Green. I'm the Director of Planetary Science. New Horizons is one of our spectacular missions in planetary science. It's going to places that we didn't know exist in my lifetime. We've discovered the Kuiper Belt. The Voyagers and the Pioneers flew through the Kuiper Belt at a time they didn't even know it existed. And now with New Horizons, after it's gone by, Pluto is now in the Kuiper Belt and on the hunt to understand these objects like we've never imagined, up close and personal. We have an exciting panel today. Let me talk and introduce our panel members. Alan Stern will talk. Marc Buie, Alice Bowman, John Spencer, Hal Weaver, and Ann Burbisher. This team has done a remarkable job, and they keep amazing me each and every time. And I know they'll amaze you today. So with that, Alan, set the stage.
Okay, thanks, Jim. Is this mic live? Yeah, there we go. Super. Okay, so 2.5 years ago, New Horizons blazed through the Pluto system and made a spectacular suite of scientific discoveries, the first exploration of the Pluto system and of the ice dwarf planets of the Kuiper Belt. And for the past 2.5 years, we've been flying farther and farther on a mission, an extended mission, which as its centerpiece will include the first ever flyby of a Kuiper Belt object. And we're going to be telling you about that object and about our flyby plans this morning. So if I can have the next slide, I think they're going to advance them from the back after my name. Thank you. So this is a little cartoon view of the outer solar system, the Kuiper Belt, and our trajectory that's shown there in yellow. And you can see where MU-69 is. It's about 1 billion miles farther beyond Pluto. It's quite a distance that we're traveling. That's as far as from the Sun to Saturn. You lose that scale on a diagram like this. As Jim said, New Horizons, which when it was selected, or at least when it was solicited, was called the Kuiper Belt Pluto mission, is the first mission to specifically explore the Kuiper Belt. And we kicked that off with the exploration of Pluto. And now, next slide, we're on an extended 5-year mission through 2021 to explore the Kuiper Belt in a whole host of ways. We are using the telescopes and imagers on board to study dozens of other Kuiper Belt objects that we pass along the way and after MU-69 to provide scientific context. For MU-69, the centerpiece of the extended mission, a ancient primordial Kuiper Belt object, which we will swoop down on New Year's Eve and New Year's Day 2019, just 55 weeks from yesterday. And then the third component, after the observations of other Kuiper Belt objects and the close flyby of MU-69, the third component of the extended mission is to understand the environment of the Kuiper Belt using our plasma sensors, our ultraviolet spectrometer, and the student dust counter that's aboard. We're actually measuring the radiation and dust environment and studying the neutral gas that perfuses the Kuiper Belt, and which is essentially the environment that all these KBOs live in and what causes their surfaces to age. So it's a very complete, very comprehensive mission. We're taking data many times per year, and at the same time intensively planning the flyby of MU-69. That flyby will begin in August with early navigational and then later hazard observations. Alice Bowman will say more about that. And then the science will be a little bit different than at Pluto. Because Pluto, we exceeded Hubble resolution 10 weeks out, and we're able to already start learning things from a great distance. But because MU69 is smaller, although we'll still exceed Hubble resolution 10 weeks out, we won't resolve the object until the week of the flyby. And it's going to be a very exciting, almost overnight experience in which MU69 will go from a point of light to a real place in the sky, a new world that humans have explored. And I'll take my last slide. I just want to point out a couple of the attributes. Besides being the farthest exploration in the history of humankind, this flyby is also going to the most primitive and pristine object ever explored. We've really never been to anything like this. Of course, we've had lots of missions to comets that come from the Kuiper Belt, but they've come down into the inner solar system where they're processed sometimes hundreds of orbits with passages by the sun, and they're much smaller. If you remember Rosetta's comet, 67P, which you saw so many pictures of from that great ESA-NASA mission, this is a much larger target. It could fit about 1,000 Rosetta comets inside itself. It's 1,000 times the size and probably about 1,000 times the mass. So this is a whole step up. It's a worldlet of its own. And to tell you more about that, Marc Buie from our science team.
Thanks. So I wanted to give you some information about what we're doing this summer. Jim mentioned that we had a very exciting summer. Boy, that was an experience of a lifetime. What we were doing was looking for an occultation. For those of you who don't know what an occultation is, it's when something gets in front of something else. In this case, our mission target, 2014 MU69, was predicted to pass in front of a star. Now, the object itself, we only think is maybe 30, 40 kilometers across. That's pretty small. And we have to make very ultra-precise measurements of where the object is, where the star is, so that we know where to put our telescopes on the ground. And if we're in the right place, the star disappears. What happened was we tried this 3 times. The first 2 times we saw nothing. It appeared at the time. Later processing showed an interesting thing that I'll mention in a bit. But this is what we saw on July 17. Now this is kind of a dry plot, but this is actually the data. There's no models here. Each one of these lines represents a cut across the system where we were watching the star. So for instance, this curve at the top called T10, the star went by the object and we saw nothing. The star was there the whole time. But on T17, the first one that has little yellow dots on it, the star disappeared for 1 second. Actually, it was half a second, if I remember right. T13, it disappeared for 1 second. Just the barest brief bit of time, the star winked out. I have to say, this was very reassuring. Up to now, we're looking at really, really faint little blip from Hubble, and you can wonder, is this really real? But boy, when it blots out the star, you know you got something. So this tells you that this is not a simple spherical object already. You don't have to do any kind of processing on this to know that there's something weird going on this object. So we've been thinking about this, trying to figure out how to put all the data together and understand what we've got. And shortly after the July 17 event, we came up with these 3 different scenarios. On the top is what we saw imagine what we saw from the occultation. They all have similar profiles that are consistent with the observations, but if you look at them from the side, each of these look a little different. One of them is a close binary, the one on the left. In the middle, it was a contact binary, so like 2 globs of ice cream stuck together. Or it could be a very, very misshapen potato-like sized object. We don't really like the potato-sized object. This kind of shape exists in the asteroid belt and is very common, but at a very, very much smaller sized object. For something this size, that's very, very strange. So which one is this? So I want to put together for you a very quick little step through our expeditions. So June 3rd, we were in Mendoza, Argentina, and in South Africa. and we had 25 stations looking for the star to disappear. I've shown 5 here right at the top, and there's more that go off the top of the graph. We didn't see anything. We thought we were in the right place, but it turns out we weren't. And now we know, we think, where this X marks where we think the object was. So what happened on July 10, we were flying aboard the Sophia Airborne Observatory over the Pacific Ocean, and we saw a little blip. Now, this took us a while to figure out that this was real, but we've been trying to figure out why, an explanation for it, because it doesn't happen where the object is predicted to be. And that's how I've drawn it off to the side, because we know that it's not where the X is. And then on July 17, we hit the jackpot. Here's all of our chords for all of our telescopes and stations. And you see the outline that I drew you before, but this is where the position is. So it's not at the right place either.
Can I ask a quick question?
Sure.
Each of these dates is a different star, right?
Is a different star, yes. And that's also part of the difficulties with this, because they each have their own errors and uncertainty in their position. But we think we've got a pretty good bead on that. So now, the picture is, we think there were 2 objects. We've got, I prefer the contact binary in this particular case, but it could be any 3 of those scenarios that I already showed you. And then another small object that sits out here and sits in that little notch that we saw in Sophia. The key here is that the satellite, the little moon, missed all of the observations on July 17. That's how I've drawn it down here, that if we'd have gone just a little bit further south, we might have seen that. But we didn't know it was there. And we definitely needed to get the big guy before we could kind of figure this out. So what we think is, we've got a contact binary orbiting around a common center of mass with another moon that sits out there. So now it's almost like we got 3 objects in one here. And this is very exciting. If you ever thought, why are we going to this little chunk of rock out in the middle of nowhere out in the outer solar system? This is going to have a lot of surprises. We think that this is probably a sign that the object itself was not a collisional fragment. We think it was made like this. And so we really are going to see something that dates back to the birth of our solar system. And so that's the final picture I want to leave you with. Now, this is not a final result. We haven't published the paper yet. The story could change next week. It's very sad to say. As Jim has been hearing, we've been changing the story a lot since July 17, but today, right here, right now, we think this is our best explanation for everything. And with that, I will pass it on to Alice.
Okay, I'm going to give you an overview of our timeline. We will be putting the spacecraft into hibernation next week, and during that time, the particle observations will continue with Pepsi and SWAP, and also the dust counter observations. In June, we will wake up the spacecraft from hibernation, and in mid-August, we will be putting the spacecraft into a 3-axis mode. This is what we use to take pictures and data collection with our spacecraft. And during this, in mid-August, we will start the optical navigation campaign and imaging distant KBOs. And you can see on the timeline that we have where we'll first start imaging 2014 MU69, and that is in early September. The optical navigation data will be used in conjunction with our DSN tracking data and our Delta Door measurements by the navigation, mission design, and guidance and control teams to determine whether or not we need to do a course correction or a TCM. Our first opportunity for TCM is in early October, and this is the first of 9 opportunities that we have. The last one is on December 22nd. We will also be doing hazard avoidance observations. Those will start the end of November and continue through mid-December. And you can see on the chart that second green dot is where we make our team decision whether or not which flyby distance we're going to use, either 3,500 kilometers or 10,000 kilometers. And that will come just a week before the 9-day flyby sequence will start. We then will go into solar conjunction right after the 9-day flyby sequence. You can see it right there. But during the solar conjunction period, the observations of the MU-69 system will continue. And then we'll go into a spin mode and be downlinking the data. So in a little bit more detail, this is what the 9-day flyby days look like. We start that set of commands on December 25th, and then on December 26th, we will transition the spacecraft into encounter mode. Our focus from the 25th through the 30th will be optical navigation, and at this point, we will be looking to see if we need to adjust the timing of our observations of the MU-69 system. We have 3 opportunities to adjust that timing, with the last one coming on December 31st. And you can see that our one-way and round-trip light times are rather long. We are 4 billion miles from Earth, 43 AU, and so you can see that it is going to be quite a challenge. We have 2 data downlinks of the MU-69 system prior to closest approach. Closest approach is January 1st, 12:33 a.m., and that's in Eastern time. And then we have 2 data downlinks post closest approach. We will be using 6 DSN stations simultaneously to uplink to our radio science instrument on board the spacecraft, and that'll occur a one-way light time prior to the observation on the spacecraft. Closest approach is again at 12:33 a.m., but we will not know until about 10 a.m. Eastern time how we fared, if the spacecraft is safe, and it looks like it's recorded all the data. After January 3rd, we will transition the spacecraft back into a 3-axis mode, take those last few observations of the MU-69 system, and then transition into a spin mode where we'll start that data downlink of all the collected data in earnest. And with that, I am going to introduce John. Thank you.
Thank you, Alice. So as Alice mentioned, we have a couple of options for our flyby because we are really entering the unknown here. We don't know what the system is going to be like. Marc has shown an example of how complex the system might be. So we're prepared for the unexpected. As we approach the system, this is the field we're going to be looking at. This is a picture taken by the spacecraft long-range camera back in September, a long exposure image of the star field where MU-69 is going to show up as we approach. And it's a little daunting. We're looking into the heart of the Milky Way here. There's an enormous number of stars. We've even got I don't know if I can point, but you can see we even have a nebula over there that's glowing on the left-hand side. It's a very interesting and scenic field, but it's also one where it's going to be very hard to see the object. So we're going to be keeping an eagle eye on that little spot right there in the yellow circle, and we expect MU-69 to become visible, just gradually brightening as we approach it. Sometime in September, we might see it in August. We'll start looking in August. And then we're really hoping it shows up in the right pixel, because if it doesn't, it means that something isn't quite right with the navigation. And so that's one of the possibilities that we will be checking, is that it's actually exactly where it's supposed to be, so we know where to point our cameras. And so once we detect it, we'll be looking for the moons that we have hints of from the occultation data. We'll be looking for maybe additional moons that might be there, trying to map their orbits. We'll be surveying the region around MU-69 for hazardous material. And we'll also be refining our navigation of where MU-69 is. If we see any surprises that would indicate that our closest approach distance of 3,500 kilometers, which is what we would like to fly, is not going to be safe or will not be able to point accurately at the targets. Then we have the option, as Alice mentioned, of diverting in as late as mid-December to a more conservative flyby distance of 10,000 kilometers, where we'll be backing off a little bit. We'll be possibly able to avoid any debris if we see there is evidence for debris, or we'll have a little bit wider field, so we'll be more confident of catching the object. So it's going to be a very interesting time around the holiday season next year, as we're learning in real time what the system is like, whether we can fly the close trajectory that we want to fly, or we have to do this deflection, and we're all looking forward to that time. I'm now introduce Hal Weaver, the New Horizons project scientist, to say a little bit more about what we'll see when we get there.
Thanks, John. Hello, everybody. So it's pretty hard to beat what New Horizons did during the Pluto flyby, but one way that the MU-69 flyby will actually do better is with spatial resolution. And for those of us who are interested in studying the geology of the surface of MU-69, seeing what it really looks like instead of this pinpoint of light, what does that surface really look like? Spatial resolution is everything. And we get that higher spatial resolution because we plan to fly much closer to MU-69 than we did to Pluto. Instead of 12,500 kilometers away from the surface of Pluto, we'll go down to 3,500 kilometers. And if you see the next slide, imagine you're on the New Horizons spacecraft flying above New York City, and you're seeing Manhattan, down here, the peninsula of Manhattan. You see the Hudson River in the middle. And this is just a comparison of the resolution that we had during the Pluto flyby to the left compared to what we're going to get during the MU-69 flyby to the right. And you look carefully, it's already pretty impressive what we did on Pluto, of course. But if you recall, we had one strip going across Pluto, just covering a small swath of Pluto at this highest resolution. We expect to get this kind of resolution to the right over the entire sunlit portion of MU-69. So who knows what we're going to see? As you saw, there's a lot of uncertainty regarding what kind of an object MU-69 is, but undoubtedly, higher resolution is always better. And it's not only better for the panchromatic images, the black and white images that we're going to take like this, but also for our color imaging and for our infrared spectral imaging. Resolution is going to be very important. So we're really looking forward to seeing the most primitive object ever encountered by a spacecraft and seeing what it really looks like. Thank you. And now I'll introduce Ann Verbisher, who will talk a little bit about the science objectives.
Verbiscer. So I'm just going to give a brief outline of some of the science objectives that will be undertaken by New Horizons when it encounters MU-69. So using this suite of 7 instruments shown on the right on the spacecraft there, we will be characterizing the geology and morphology of the surface, looking to see whether there are any craters on this body. We certainly expect to see craters. Possibly there could be grooves, as you see on the small Martian moon Phobos. Also, using stereo imaging, we'll be able to investigate the topography and look at elevation on the surface. We'll also map the surface composition with the near-infrared spectrometer, searching for possible ices on the surface, such as we saw on Pluto's small moons that have ammonia and water ice. Also carbon monoxide that we saw on Pluto, any methane, which is covering the surface of Pluto quite a bit. Also, what makes MU-69 dark and red? From the occultations this past summer, we learned that its albedo is quite low, about 0.1. And from Hubble observations, we've learned that the color of MU69 is quite red, much redder than Pluto itself. Also, as far as the structure of the whole system, if we have a system here, like as the occultation results suggest we might, is this a single body? Is it a binary, contact binary, close binary? Who knows? We'll be searching for and studying satellites and rings. Is that moon really real? Is it there? And are there any others? Certainly in that system there could be more than one. And then looking back, once we passed MU69, and looking back, backlit by the sun, back at MU60 at the body, searching for any possible coma, which would be produced by an atmosphere or gases around the body. And that's all I have. Yep.
Great. Okay, so now we'll open it up to questions.
Hi, my name is Syd Perkins. I'm a freelancer. Got a couple of questions. What is your flyby speed and what is the light level out at MU69 projected to be, and how do those constrain your observations, if at all?
No, the flyby speed's a little higher, a little above 14 kilometers per second, and almost precisely what it was at Pluto. So we know how to do that. The light levels are about half the light level at Pluto, or about 2,000 times fainter than broad daylight on the Earth. And all of our cameras and spectrometers, all the sensors on board were built to operate even farther out in the Kuiper Belt, so the results should have very high signal to noise.
Next question.
Jeff Faust, Space News. Any opportunities to do additional occultations or other measurements to try and constrain whether it's a contact binary or whether that moon is really there?
We have one more opportunity that I've identified is on August 4th, 2018. It's not the best spot in the world for us to be doing this, but it's not hopeless either. Crosses over northern South America, starting in Colombia, across Venezuela, and then off into the ocean. And then it makes landfall again in Africa, passing the coast of Africa just south of Dakar, and on into Mauritania and Mali and Algeria. And we are actively talking to people in both Senegal and in Colombia about pursuing this. It will be a very difficult observation to try and get both components in the same event. We need a very dense network of telescopes and a very broad coverage to ensure getting both objects. It's weird to say that I think it would be easy to get the main primary object. It's not easy, but comparatively, getting both is going to be a really, really big stretch. But I think it's worth giving it a shot, but we're going to see how it goes.
Yeah, and if anybody can do it, it's Marc and his team. The occultation success with Sophia and with the ground-based picket fence that Marc set up was the toughest occultation ever attempted, and they succeeded. But if we don't succeed, whether it's the weather or something else, next August, then we will find out the answer on approach. We will find out in the final days as we close in on MU69 whether this satellite is real or has company. It's going to be exciting.
Next question.
Thanks. This is Ric Feinberg from the American Astronomical Society. I think my question is probably for Hal. You were comparing the resolution of what you'll see at MU69 versus what you saw at Pluto, and you suggested an improvement of a factor of better than 2, but you earlier said that we're flying almost 4 times closer, so I'm just confused as to the math.
Yeah, it's when you do the observations, everything is happening on a very compressed and fast time scale. So when we take that highest resolution image, we're a little bit farther away than what you could potentially do. just because of the nature of everything else that we want to try and fit in.
Christoph Seidler, Spiegel Online. Maybe that the answer to my question showed up already in Alice's timeline and I just didn't get it, but when do we actually get the first high-res image? When can we expect that?
I'd be happy to talk to that, and John should probably add to what I have to tell you. MU69 will appear as a point of light, or if there are satellites, multiple points of light, until literally the last day or two. And then it will be just a couple of pixels across. And it will only be after the flyby on January 1st, 2nd, and 3rd that spectacular images will start to come to the ground that, as you saw from the earlier presentations, will even greatly exceed the resolution at Pluto. John, want to add something?
Yes, it's going to take a little while to get the very best pictures down because we have to get some of the lower resolution ones down first to figure out exactly where it was, and so that will tell us which of the highest resolution pictures to bring down. But we expect to have pictures that might be 100 pixels across, give us a real idea what this world is like within a couple of days of the flyby, maybe sooner.
Okay, I'm just continuing. I'm sure you do have a pipeline, so what date should we mark in our calendars?
You should spend your New Year's Eve with NASA at the Johns Hopkins Applied Physics Lab. And by the way, we're planning to allow the press to bring their families as VIPs to the flyby, so you don't have to choose between your family and covering this historic flyby. And then the important scientific results will start to pour down to the ground on the 1st of January, and then even more on the 2nd and 3rd of January. So come and spend the week. Someone said spend your Christmas in the Kuiper Belt. It's going to be exciting, and there's not going to be anything like it again. There's no planned further exploration of the Kuiper Belt. No mission back to the Kuiper Belt yet.
Are we all going to get a lump of coal that year?
Maybe 2 or 3 lumps of coal.
Harvey Lyford, freelance. It's sort of a two-part question. I don't know what the circumference of the solar system is at that distance, but you've got to assume that you've been extremely lucky to find this following the trajectory which took you past Pluto, but presumably any other trajectory might have also encountered objects like this, and have you speculated about how likely it is that this is unique or common or anything in between? And secondly, after the flyby, I presume it just keeps going like Voyagers and will exit the solar system at some point?
All right, so I'll take the second question, but first I'd like Marc and John, who led the search for MU69, and Hal, if he wants to chip in, because he was a major part of that campaign as well, to talk about some of the predictions that we had before for how many targets might be out there with a Hubble search, and then what we turned up.
Yeah, we actually started looking for this back in 2004. We thought, it's going to be faint. There's a lot of stars, but this will be easy. There's lots of things out there. And 10 years later, we started to get a little worried, I have to say. So were we extremely lucky? No, because there was one to find out there, but we were a little bit lucky. There was nothing about this that was a slam dunk that we were guaranteed and assured to find this object. But it was just right on the edge of what we could do. You want to?
Yeah, I'll just add that, excuse me, we think there are hundreds of thousands of objects the size of MU69 out there in the Kuiper Belt. And so the odds of us having one close enough for us to reach are actually reasonable. In fact, we had another one that was a little bit further away that we could have reached if we'd chosen to, that we found with the same Hubble campaign. So one of the exciting things about MU69 is that it's probably a very typical member of the Kuiper Belt in this size range. And so what we learn about MU69, we're going to be able to extrapolate to hundreds of thousands of other objects that are representative of this primordial material that the solar system was made out of.
Okay, so part 2 of your question was what happens next, more or less. So the spacecraft is flying on a hyperbolic trajectory, which means that it's got enough speed to completely escape the solar system like the Voyagers and the Pioneers before us. And there's nothing that can slow us down. So it's flying out of the solar system. It has the power and the fuel to operate for probably into the mid-2030s, possibly longer. And there's a lot of good science to do, both planetary science after this mission and also applications for astrophysics and heliospheric science. So I expect that New Horizons will have a series of successful proposals to NASA over the years and continue in the great tradition of the Pioneers and the Voyagers to keep exploring further and further outward. There's a small chance that we might find another object to fly by, but our fuel supply is very low. And so the great probability is this would be the last flyby for New Horizons. That said, we will certainly look, and you'll hear more about that around the time of the flyby. I think the one other thing that I want to say is that much like Pluto, it takes a long time to get this torrent of data that we're going to take on the close flyby back to Earth. In fact, because we're farther out, the data rates are even slower than they were at Pluto, and it's going to take us the rest of 2019, all of 2019, and most of 2020 to get all the data to the ground. We don't expect to finish up the data transmit until August or perhaps September of 2020. So the news will just keep raining down from the Kuiper Belt.
Hi, Ken Chang, New York Times. From the few wisps of data you have from the occultations, can you put any constraints about the size of this moon or its orbital characteristics?
Well, these are kind of notional numbers. We certainly don't have an orbit, okay? So we know that the primary object is like 20 or 30 kilometers across, depending whether it's the long axis or the narrow axis. The little guy is consistent with an object that's maybe 5 kilometers across. Could be a little bit smaller, could be a little bigger, but that's roughly the right ballpark. It's roughly about a factor of 10 down in mass from the primary, so think about the difference in mass between Pluto and Charon. It's about the same thing there. So those are very rough numbers, but that's kind of the ballpark we're talking about. And then an orbit period could be, an orbit period of 2 to 4 weeks is consistent with the scenarios that we're looking at. Of course, we don't know what the densities are and what the total mass is, but those are kind of ballpark numbers.
How much distance is between them, perhaps?
Oh, the distance, yeah. That's something like 200 to 300 kilometers.
And the X where you marked where you thought where the center of mass was, how did you calculate that?
That is based on the orbit, and that comes from Hubble Space Telescope images of the object, starting from discovery in 2014 up to our last measurement that we made is in October. And that is all tied together with the star catalogs from the Gaia mission. We've got a special pre-release of their new catalog that's going to be made public. The entire catalog is going to come out in April. This is a fundamentally powerful and brand new data product. I mean, it improves on the positional knowledge of stars at 1 or 2, 3, sometimes 3 orders of magnitude better than anything we've ever known. This whole thing would have been absolutely impossible without the support from the Gaia mission. And it's a little nerve-wracking because we are really into a frontier of a new realm of positional astrometry, and I have been spending the past 6 months fixing all my code for all the little assumptions I made along the way that says, we never will measure anything that precise, and we do now. I'm learning all about this new term called micro arcseconds. So for those of you that like units, that's a fun number to wrap your brain around.
Hi, Syd Perkins again. Quick question related to some of the observations you said you were making along the way in terms of dust and gas, a neutral gas. Is that primordial or is it sublimating from some of the objects? Is there any measurements you can make to tell? Is it a little of both?
Yeah, it's a little both. The gas, both the charged particles and the neutral hydrogen, that fill the Kuiper Belt also fill the whole of the heliosphere. And the ultimate origin of most of that stuff is the sun. And it's an outflow from the sun that begins with a solar wind and only terminates much farther out with the boundary of the interstellar medium. But the dust impacts are primarily from objects in the Kuiper Belt that collide with one another and create a background dust population.
Christoph Seidler again. I understand that you're having a competition for an informal name for the body. I also understand that you have extended the deadline. Will we talk about MU69 until the day you get there, or will we have an informal name before that? What might that be? What are the best contestants? Thanks.
Good try. Yeah, so we did extend the deadline because the voting people were really enjoying doing it, and we wanted the maximum public participation. We had over 31, I think it's actually over 34,000 name nominations to choose from, and many more votes than name nominations, obviously. The voting concluded last week, and then we're now going to go through a careful process as a team and with NASA, with the NASA Science Mission Director to choose that nickname and then announce it in the early part of next year. Jim Green may want to say more.
And it'll be a good one.
Hi, Ric Feinberg again from the AAS. If I saw right on Alice's charts, I think you said that the asteroid or the KBO goes into solar conjunction right after the flyby?
That is the spacecraft.
The spacecraft, yes. Okay. So does that affect your ability to get the data back early on? And sort of how long is it before that's not an issue anymore?
Yes, it does affect our ability to get the data down because solar conjunction, limits the commandability and the data rate coming down. We could go to a very low data rate and still get health and safety data if we choose to. But what that means is it's actually a bonus for our instruments because they can take very long observations and not have to interrupt those observations with DSN tracking. And so that's actually a good thing. And right after solar conjunction, we'll be putting the spacecraft into a spin mode. And what that does for us, it allows us to turn on both transmitters and essentially increase our data downlink rate by about 2 over what it is in a 3-axis state. So at that point, we'll start in earnest bringing a lot of data down.
Yeah. Let me just add to that every year in early January, the spacecraft goes through solar conjunction. The Earth and the spacecraft are on opposite sides of the sun. And for a period of 4 or 5 days, Alice could give a more precise number, we have to suspend data downlink. So we'll have about a week, not quite a week, after the flyby to start getting data to the ground. And we're already planning precisely which observations we can fit in during that week. And then there'll be a pause, and then again we'll come out after 4 or 5 days and we'll spin up, as Alice said, and turn on both transmitters, which doubles our data rate, as she also said. And then the long downlink that'll stretch across 19 and most of 2020 will begin.
And then a related question, presumably the object itself is also in the general direction of the sun. Does that limit what kind of ground or space-based observations might be done during the flyby? Because I know during the Pluto flyby you had Hubble looking. Will anybody else be looking at this object when you're flying through the system?
Pluto was so popular, every spacecraft in the solar system wanted to take a picture of it in the distance on flyby day for New Horizons. It was like this great community, upwelling of scientific spacecraft stationed all around the solar system. But for MU69, it will be lost in the daytime sky. It's very faint anyway, and really only the Hubble has the capability to routinely observe it, and the Hubble can't observe at these extremely low solar elongation angles. So when we fly by, we'll be the only facility that's taking data.
Nulla Red, freelance. So you mentioned that New Horizons is going to be looking at other Kuiper Belt objects as well along the way and afterwards. Will it be able to see if any of those have any moons similar to MU69, or will that be not within the capabilities?
John, you want to take that one?
Sure. It's a good question because that's one of our goals, is to look at some of these other objects that are a few million miles away, not nearly as close as MU69, but they're close enough that we will be able to get images of them that are more detailed than anything that the Hubble telescope can do. And so we'll be looking mostly whether they should just appear as points of light, but we will be looking for moons that might be much too close for Hubble to see around some of these other objects. And so we'll be able to do some really unique stuff on these other worlds, even if we don't get within more than a few million kilometers of them.
Yeah, Jonathan Amos, BBC News. There's some evidence, I think, from Comet 67P that it formed in quite a low energy environment, the way that its internal structure was put together. Presumably, is that something you can compare and contrast with this bodies?
Yeah, I was a part of the Rosetta mission, and what you say is correct. And we'll be certainly looking at MU69 and its surface geology and the overall object's morphology to try and understand the accretion environment. But the satellites that we may find, which we already have hints of, could also tell us about that accretion environment. Let me give you one exciting possibility. I can't put a probability on it. Maybe it's very unlikely, but if there were only one satellite out there and small, as Marc's data suggests, from the Sophia Airborne Observatory, then it's kind of a needle in a haystack, and it'd be unlikely that Sophia would just happen to trip over it. So this might be the harbinger. It might be a hint that there is actually a swarm of satellites around MU69 that could be very interesting from the standpoint of understanding that accretion environment.
You remember what the Goosebumps in
Paul
in
Weissman.
67P?
Yeah. I was just thinking about answering that question and ending up in tabloids tomorrow. So let's not couch things as dinosaur eggs.
You know what I mean? 67P is built
From subunits. Yeah, and that's what I meant about looking for the morphology in this guy. Just whether it's Marc thinks it's bilobed. I think it's an orbiting binary with an exterior satellite. We'll take a look at all that, but we'll also look at the individual bodies to see if we can find any evidence in color units, compositional units, or in their structure and morphology that they were built in a bottoms-up way from smaller bodies. And that's one of the things that I think New Horizons has a chance to greatly contribute to scientifically, because this object has always been in this very low collisional environment and very cold, basically 40 degrees above absolute zero environment. So it should have preserved a record of that accretionary time better than anything that's ever been observed by any spacecraft mission in history. And that's what makes us so excited about going to it.
Okay. Hi, Mary Beth Griggs, Popular Science. Back here. I'm curious, with this new potential moon out there, does that change your calculations for flyby trajectories and orbits at all? And what is that potentially going to look like?
Well, John to my right is the person in charge of the detailed flyby planning, and all of the flyby instrument plans and scientific objectives fall under his wing. So that's John's question.
Yeah, we've always had in our plans the possibility that it might have moons. And there's two things you have to worry about from moon. One is you'd like to take pictures of that moon. And so we have in our plans what we call a retargetable, which is an observation that only a few days before encounter, we can tell the spacecraft, okay, at this time, go look at this place over here. And so it could go, and we can update that position very late in the game. So hopefully we could get a close-up picture of the moon if it wasn't going to appear in our other scans. The other thing is if you have a moon orbiting MU69, it makes MU69 wobble. And so where you're pointing your cameras at the main body is going to change. And so we've done a lot of simulations as to how well we can predict what that wobble is going to be so we can adjust our pointing late in the game. And so that's going to make the last few days of 2018 very exciting as we do those calculations, we figure out what the wobble is, we upload that information to the spacecraft, and so that we'll have correct targeting for our observations.
We're actually out of time, but if you guys want to stick around for a minute, answer the last one or two questions. Thank you very much to our panelists, and we'll reconvene at 1:45.